Yeah. Okay, welcome to Strong Field Laser Physics. Today we will bring together our two perspectives that we have of strong field ionization, namely the photon picture on the one side and the wave picture, which is essentially given by our classical model. Well, so far our classical model is really a particle picture, but we will actually turn it into a wave picture today, and then we can reconcile it with the multi-photon ionization model. Okay, last week we moved from last week we went back to discussing multi-photon ionization. Oops, sorry. Yeah, and we looked at this formula here. Maybe this is a bit small to see, is it? Yeah, so we looked at the position of the ATI peaks, to be precise, and namely, I think I just write it here one more time. Okay, so we have so far the kinetic energy of the photoelectrons in the photon picture we considered as this here. Yeah, so this is the energy absorbed from the field, n, the energy of n photons, and then the kinetic energy of the free electron would be given by this formula. So you simply subtract the ionization potential of the atom. And last week we extended this picture a little bit, namely by including what quantity? Yes, please? The ponderomotive potential. And why did we have to include it?
Because it's an additional potential that the electron feels when it's outside of the
Yeah. So one could say there's an additional potential given by this oscillatory motion that the electron also needs to enter. Yeah, and therefore we expect a shift of the lines given by the ponderomotive energy. And we saw that this has quite profound consequences. And well, maybe show the laptop only for now, because we want to see these here in large. So this experiment summarizes a substantial number of these effects quite well. This first, the uppermost image here, this uppermost electron spectrum, this was recorded at a low intensity with a long pulse, and one observed narrow lines of ATI peaks that, well, decrease as the energy increase. And then the experimentalists measured two more spectra at a somewhat higher intensity, and one time using the same long pulse. And what they observed was, well, more ATI peaks at higher intensity. This first ATI peak here disappeared, and but the position was conserved. Then they repeated the experiment with a slightly shorter pulse, and they observed that the peak positions redshifted. They moved to lower energy, and they also broadened. Yeah, so these are quite some effects for not so big changes in the experiment. Now, how can we understand this? If you go also show the, yes, exactly. Yeah, so this picture contains most of the explanation, namely at low intensity. Yeah, so for example here, so this shows the energy of the, well, actually the binding. This is an energy diagram showing the binding energy, actually the effective binding energy consisting of the ionization potential plus the ponderomotive energy. Yeah, and this is here the ionization limit. And then as the intensity increases, this effective ionization potential also increases. Yeah, and therefore we can expect this redshift. And yeah, so this redshift, this is actually only observed for the shorter pulses, but there it is there. Why it's not observed here, we'll see in a minute. But what is observed here is that this first peak here disappears. And that effect is called a channel closing, and it can be explained by considering an intensity where this effective ionization potential moves so high that these 5 photons that were sufficient to ionize here are then no longer sufficient and don't promote the electron into the continuum. Therefore, the lowest order peak disappears. And we talked about the redshift, which is present for short pulses. So the 2 questions remain, namely, why is the effect? Why do we not observe the redshift with long pulses? And second, why do the peaks broaden with short pulses? Yeah. Who has an idea what the underlying? So the underlying physics is actually very similar. Who has an idea what they are? Yeah, so the answer that we heard was I repeated for the online viewers. So with long pulses, there's enough time for the electron to gain energy from the field, from the ponderomotive potential, yeah, and then it can actually roll down the hill and get out of the focal region, and it regains this energy from the ponderomotive shift. Yeah, very nice. Okay, so what about the other question? What's happening for short pulses? Yeah, so for short pulses, we also consider the focal volume as depicted here. Yeah, so this shows the color indicates the intensity and therefore also the ponderomotive energy. And since we integrate, so our measurement integrates over more or less the entire focal volume, we will actually always observe many ponderomotive shifts. And integrating over these, therefore, do not simply lead to a peak shift, but also lead to a peak broadening. And that's what we observe in this measurement. By the way, the right plot here, this shows the measured peak position as a function of intensity, showing clearly the redshift that we discussed. The channel closing, yes, sure. Yeah, so if let's go, we need this one on the iPad. Yeah, so here, a channel closing occurs when the effective ponderomotive energy, the effective ionization potential, namely the ionization potential plus the ponderomotive energy, surpasses the energy that is contained in, say, an n number of photons. Yeah, so here in this example here, 5 photons are sufficient to overcome the ionization potential at low intensity, and then at higher intensity this is no longer the case. And that precise spot where this happens, so that would be here, this would be called a channel closing. Yeah, and in the measurement where we do not see the peak shift, nevertheless we observe the channel closing. Yes, because once the electron has reached the continuum, it gains all that energy, and brings back the peak position there. But the one that's driven out with, well, the number of photons that this peak here corresponds to, just doesn't get out. Yeah. Well, actually, you do see a little bit of signal here in this region. And the reason for that is, again, because there are low intensity areas in the focus where the channel closing has not taken place because of the lower intensity. Yeah, and then you get a little bit of signal there. Yeah, so these. Yes, exactly. At higher intensities, if we keep increasing the intensity, the second peak would also disappear. It does not happen, however, for short pulses, because for short pulses, it doesn't actually move out of the laser focus. By the way, the difference here in the pulse duration is not that big, right? It's not even a factor of 3. So whereas here, the electron really has sufficient time to completely move out of the focus, here it very likely moves a significant portion. Yeah, so we're not yet in the region where the ponderomotive acceleration out of the laser focus does not take place. This is, however, reached for femtosecond pulses, provided they are not too intense. Yeah, so when you go up to relativistic intensities, then the electron actually rapidly leaves the laser focus within just a few femtoseconds, and this can really accelerate the electron to very high energies. And then there are more intricate effects that take place there as well. But this is not topic of this lecture. Yeah? If you want to know more about this, you want to join the lecture of Professor Kaluza. Anyway, there's an exception to these ponderomotive shifts that occur also in short pulses, namely in femtosecond pulses, and these are Freeman resonances. And this measurement here, I showed this in the seminar last week. This shows very nicely the two effects. Yeah, so you have here the electron yield plotted as a function of the kinetic energy and the peak intensity, and it's a continuous measurement. And then you see that there are diagonal lines. Yeah, so these would be the regular ATI peaks, which experience this shift, this ponderomotive shift, and you also see those straight lines here, which correspond to the Freeman resonances that do not shift. And the explanation for the invariance of the Freeman resonances is that they originate from Rydberg states, which experience essentially the same ponderomotive shift as the continuum. So that's shown here. Yeah. So this is the continuum, and here we have the Rydberg resonances. So this distance here remains essentially the same, and so no matter at what intensity the ionization takes place, the final energy is the same. Okay, so so much for the revision. So today, as I mentioned, we will look into bringing together these photon picture considerations with our classical or then semi-classical model. So we will turn our classical model into a semi-classical model. Okay, so the first lecture for today will focus here on these qualitative considerations. It's titled De Broglie action and phase, and then we will actually analytically calculate the peak position of the ATI peaks in the second lecture for today. Okay, please switch to the iPad. Okay, so I prepared here, well, the heading. So we're dealing now with interference effects, and we want to first discuss this qualitatively. So let's begin with a little motivation. And well, the motivation is, of course, what we just discussed, namely that we found that the ATI peak position is given at, well, by this formula here. We found from the above considerations that the ATI peaks are found at E ATI equals n times h bar omega, where n is, of course, the number of absorbed photons, minus EIP minus UP. And this could be called an effective EIP. Now, however, our classical model that explains the shape of the spectra does not show any ATI peaks. Does not show any ATI peaks. Okay, so now how can we get the ATI peaks? The question is trivial because I gave it already away. Yes, of course, interference. Mentioned this many times. So what's actually interfering there? And what's interfering? How do we get interference into our classical picture? We calculate electron trajectories, and now when you talk about interference, you can always consider the double slit experiment. So you have two pathways. The electron has two pathways to interfere, to take, and then these two pathways interfere and give the final result. So something similar must happen here. And for this, now we're actually considering the electrons as de Broglie waves, right? So they have a certain wavelength, they have a certain amplitude, and they will require a phase. We'll get to the phase in a few minutes, but let's first consider what's actually interfering here. Yeah, so the ATI peaks must be a result of interfering de Broglie waves emitted at different times. Yeah? So emitted at times T naught, T0 n. Yeah? And to get an understanding of this, let's quickly draw our field. Okay, so we typically draw a cosine-like field. E of t, and now, okay, well, maybe let's also draw the vector potential. The vector potential would now have a minus sign-like shape. So it goes through 0 here, it goes through 0 there, there. So something like this, yes? And this is here now A of t. Yeah. Okay. So then now we'll put one time t0 here. So maybe that's this time at that vector potential. Now, what's interfering with this? So if you have a double slit, where would be the second slit? After what? After a cycle, after an optical cycle. Yes, precisely. So that would be here. Yeah, and at that time, and then again somewhere over here, where I didn't draw the field anymore. Okay, and what about this one here? So this has the same vector potential. Would that also interfere? Yes, perhaps. Yeah? So let's put a triangle here, and now it gets a little complicated. To make it not too complicated, I'll draw. I'll draw a horizontal line here, and now all these times, yeah, where this. Oh, I guess this cannot really. I make it a bit darker. Okay, so one more time, the horizontal line. Yeah, so all these times here where this horizontal line intersects the vector potential, these would be times at which which the electron would have the same final energy, or the same final drift momentum actually. The same final energy, of course it will also have up here. Yeah, would these times here, what about these times? Would they interfere with those down here? Yeah, they have the same energy. Would they interfere? They would not interfere, yes. And why not? There's pi over 2, yes, but why? This is not the reason why they wouldn't interfere. Why would they not? The direction, wonderful, yes. The direction is in the opposite, and therefore the electrons would not interfere. Okay. Yeah, so we have here, well, so I like to draw this with circles and triangles, yes. So you have these circle times, and you have these triangle times, and all of them, they would interfere. Okay, so let's write this down. A, only electrons with the same final state. Yeah, that's actually the general condition, and well, the state of free electron is well described with its momentum. State interfere. There are two of which, by that I mean two trajectories that lead to the same final momentum in each cycle. Yeah? So these are the circles and the triangle times. Okay, so now how do we get the periodicity of H bar omega in the ATI spectrum? Well, we have two such times, but if we only consider now the interference between the circle times and the triangle times, then we have a periodicity of T, one optical period, and that of course corresponds to an energy spacing of H bar omega. Considering interference of circle with circle or triangle with triangle, yes, triangle with triangle, we have a periodicity of T, and therefore energy spacing H bar omega. Now, what about the circles and the triangles? Can they interfere as well? Yeah, of course they can. And what does that correspond to? So these are additional interference effects that we will discuss after looking at the ATI peaks. Yeah, so circles with triangles can also interfere. And these are then called ballistic interferences or intracycle interferences. So why intracycle? Because they're both within the same laser cycle. So they're both within the same laser cycle. And why ballistic interferences? So if you, as you know, when you do a diagonal throw, there are always two angles that lead to the same distance. Yeah, there's the flat one, and there's the steep one that goes like this. And so the cannoneers, they actually take advantage of this. So they shoot a first bullet like this, that's in the air for a long time, and then they shoot a second one lower, and then both cannonballs hit the target at the same time. And this is why they're called interference. Well, I didn't really make the connection to the trajectories yet, right? So one of these trajectories, namely this one here, where the field is decreasing, this is a recollision trajectory. So it first goes the other direction and then comes back. And this is a direct trajectory. So it will hit the same target, namely it will have the same final state, but it's shorter than the one that first goes into the opposite direction and then comes back. Okay. Then we can actually make an analogous discussion for high harmonic generation. So in ATI we have the periodicity of h bar omega, and in high harmonic generation, what's happening there? Write down. So in high harmonic generation, the electron needs to recollide. So we only have either circles or triangles. However, the high harmonics don't care whether the electron went out this way first and came back, or it went out that way and came back. So it doesn't care about direction. So we have these trajectories here that I asked about earlier on. These trajectories here, and they will also interfere with this. And now, these actually go away, the triangles, because they don't recollide. So they're here where the field is increasing rather than decreasing. So this is not drawn very well. This would be here close to the zero crossing. Anyhow, they do not recollide. So there are two trajectories that lead to recollision in each cycle. And so the periodicity is T over 2. And therefore the spacing is 2 omega. Okay, so an analogous argument can be made for HHG. Here, the electron needs to recollide, but HHG does not care about the direction. And therefore, the temporal spacing is T over 2, and therefore the energy spacing is 2 h bar omega. And why is it only odd harmonics and not even harmonics? I could, if I just find the spacing of 2 omega, why is it not even harmonics? Well, the first harmonic is already there. And so in order not to violate this condition, it has to be odd harmonics. Odd harmonics only. Okay, so this was almost the entire qualitative part. So now how do we actually do this in practice now? How do we calculate interference in practice? Yeah, so we if you have, well, so if you think of a double slit again, yeah, you assign a phase to each of the two trajectories, and then you can sum over the trajectories. You can find conditions for an interference maximum and an interference minimum, and here we have to do something similar. Yeah? So our electron trajectories need a phase. And what about the amplitude? Do we have an amplitude already? Yeah, of course we have an amplitude, and the amplitude is given by the tunnel probability. Yes, actually the square root of the tunnel probability. That's the amplitude of our electron waves. Yeah, so each trajectory has an amplitude and a phase. The amplitude is the square root of the tunnel probability. Yeah, the square root because we can only measure wave function squared. So if we square the square root, we get the tunnel probability back. So if we have just a single trajectory, yeah, then it's simple. And we just square it and it's done. Okay, yeah, so our electrons need a phase. A, yeah, so they have an amplitude and times EI phi, and then the amplitude is given by the tunnel probability, square root T of T naught is the amplitude of the trajectory launched at T naught. Okay, so and how we get the phase we'll discuss in a minute, and then now how do we now we need to, at the end we want to calculate the total yield at a given momentum. Yes, yeah, and then the total yield at momentum P will then be calculated as, yeah, so we sum over the trajectories. So maybe I write it like this. Yeah, so we sum over the times T naught n. Yeah, similar to here we wrote that the ATI peaks must be the result of interfering the Broglie waves emitted at times T naught n. So there are equivalent times. So there's here T naught 1, T naught 2, T naught 3, and so on and so forth. These are all the equivalent times. So this sum here is the sum over the equivalent of all equivalent times. Sum over all equivalent times. Yeah, and then this would be the batteries. So, by the way, so this is how we did it so far, right? We simply summed up all the yield of all the different trajectories. Now, actually, previously we summed A squared, right? Yeah, A is T naught. So A squared is T. That's the tunnel probability T. And so previously we simply summed up all the A squared. Now we sum over the A's, and we also need to consider the phases. Yeah, e to the I phi t naught n. And then at the end, of course, we need to take the modulus squared. And this would then be the yield for a given momentum of all equivalent times leading to final or drift momentum P. Okay, so this would be a coherent sum rather than what we previously did, an incoherent sum. Now, what we do need, however, is how to calculate this phase. Yeah, so from quantum mechanics, we know these phase factors. Excuse me. Yeah, so if you, in the wave, so the phase of a wave function is given by its energy, right? Yes, so we know we have these phase factors. Well, I write it out in a second. Yeah, so quantum mechanics. From quantum mechanics, we know phase factors exponential minus I e t over h bar. Yeah, so if you have a wave function that's associated with a certain state, its phase will oscillate like this here. But now we don't have a state, but rather we have a trajectory, and then what takes the place of the energy times time is actually the action of that trajectory. Yeah, and this is related to the Feynman path integral formulation of quantum mechanics. Yeah. Here, the phase factor can be expressed as e to the minus I s over h bar, where s is the classical action of a given trajectory. Okay, so in the script you will find a few hand wavy arguments on how you can make this plausible to yourself, but I will skip these here in the interest of time, because the second part, this will actually take a bit of time. Yeah, and we can actually use now the question is now, how do we obtain this classical action? And that's simply given by the integral over the Lagrange function. Yeah. So s of x of t. Yeah. So x of t is the trajectory, and then we want to calculate the action for this trajectory, and that's given by an integral over the Lagrange function. And the Lagrange function depends on the position, on the momentum or velocity and time of a trajectory, where L equals T minus V, so that's kinetic energy minus potential energy, is the Lagrange function. Yeah. And in the second part of the lecture, we will now actually calculate the Lagrange function for two different trajectories, and with this find the action for the two trajectories and compare the two and find the relative phase And then we can make a condition for an interference maximum, which would then lead to an ATI peak. I hope you could get an impression of how you can assign phases to the trajectories, or are there questions about it? No questions at the moment. Then we close this first lecture and we'll continue with the second one in a few minutes. There's the question, yes.
So how can we connect the periodicity of the emission and the energy spacing? So we have two situations. One is the periodicity is T, and we have the energy spacing which is extra omega, and another is 2 extra omega. So how can we get this energy spacing? So
How can we relate the trajectory to the interference? Yeah. So first, the first step is to find all trajectories that lead to the same final momentum. Yeah. So this is what we already did so far, but the only thing that we now need in addition is to calculate the phase for each trajectory. The energy spacing, yes. How do you get the energy spacing from the time spacing? So this is essentially just a Fourier transform. Yeah. So if you do a Fourier transform, then you can go from time domain to frequency domain. Yeah. And frequency domain is equivalent to energy. Yeah. And then a spacing of T would correspond to a spacing in energy of omega, because it's simply 2 pi over T. Yeah. And by the way, you can do we talked about, or Professor Paulus talked about laser-induced electron diffractions a couple of weeks ago, yeah, where we were considering a molecule with a certain internuclear distance. And then you have two scattering centers that are separated in space by r, and this leads then to an interference in momentum space. And then there you observe a spacing of 2 pi over this distance in momentum space. Yeah, so it's equivalent. Okay, yeah. Then we close this first session, and or you've done it already. Okay, good.